There is a planet 40 light years from Earth where the ground is made of molten rock, not lava flows covering a solid surface, not a volcanic region like the Hawaiian Islands where magma occasionally breaks through the crust. The entire surface, a global ocean of liquid rock, thousands of kilometers across, kilometers deep, with no solid land anywhere, just magma, permanently, churning under an atmosphere that should not exist, emitting light bright enough that it glows in the dark of space without any help from its star. And this planet is not the most disturbing planet in this video. In the past 30 years, we have found 5,700 planets outside our solar system. Most of them are broadly comprehensible. Cold gas giants, warm rocky worlds, icy mini-Neptunes. But some of them are wrong in ways that go far beyond unusual. Wrong in ways that make the word planet feel like a category error. Wrong in ways that, once you understand the physics, make it genuinely difficult to accept that a place like this can exist under the same laws that govern your atmosphere, your weather, the orbit of the moon. This video is about the most deeply, structurally, fundamentally disturbing planet in the known universe. But to understand why it earns that title, we have to visit several others first. A progression of increasingly wrong worlds, each more disturbing than the last, each one a step toward the planet that should not exist. We start with glass. Chapter 1. The Blue Planet. That will sand. You to nothing. Here is a fact that sounds like it was written to be unsettling. The most Earth-like color in the observable universe belongs to a world that would kill you in 1/100th of a second. The planet is HD 189733b. It sits 64.5 light years from Earth, orbiting a star in the constellation Vulpecula. It was first detected in 2005, when astronomers watching the star noticed it dimming slightly every 2.2 days, the signature of a planet passing in front of it. That short year was the first signal that something unusual was going on. 2.2 days. Not 365. Not even 30. 2.2. Let's hold that number for a moment before we get to the violence, because the orbital period alone is enough to dislocate your intuitions. Every 2.2 days, HD 189733b completes a full journey around its star. While you are working a long weekend shift, this planet has gone around its sun once. In the time it takes Earth to complete a single orbit, 1 year, the unit of time around which human civilizations organize their calendars, their harvests, their seasons, their festivals. HD 189733b has completed 166 years. It is an old planet orbiting a middle-aged star, and by the calendar of its own orbit, it has experienced something in the range of hundreds of billions of years. The year is meaningless at 2.2 days. So is the idea of seasons, of a winter that ends, of a summer that follows. There is no orbit-driven change on HD 189733b, just the permanent, unchanging, locked geometry of one face toward the star and one face away. The reason the year is that short is the reason the planet is disturbing. HD 189733b orbits its star at a distance of about 4.4 million kilometers. Mercury, the innermost planet in our solar system, scorched, airless, blasted Mercury, orbits the Sun at 58 million kilometers. HD 189733b is 13 times closer to its star than Mercury is to ours. At that distance, the star's gravity has permanently locked the planet's rotation to its orbit, the same way the moon is locked to Earth. One face always toward the star, one face always away. The dayside temperature runs around 1,200 degrees Celsius. The night side, permanently shaded, never seeing a sunrise, sits at around 950 degrees. Not cool, not cold, 950 degrees Celsius in the dark. And those temperatures matter because what they drive is wind. The 250-degree difference between the day side and night side of HD 189733b creates an atmospheric pressure gradient that is extreme by any planetary standard. To equalize that gradient, the atmosphere moves. It moves at approximately 9,000 kilometers per hour. Stop and hold that number for a moment. The speed of sound in Earth's atmosphere is about 1,225 kilometers per hour. The sustained global wind speed on HD 189733b is roughly 7 times the speed of sound. Not gusts, not peak speeds. Continuous global permanent motion of the entire atmosphere at 7 times sonic velocity. The planet doesn't have weather. The planet is weather. A solid ball of physics wrapped in a single continuous body of screaming atmosphere. To feel what 9,000 kilometers per hour actually means as a physical environment, consider what that velocity does to matter. A human being standing in a wind of 100 kilometers per hour, a severe storm, experiences a force that makes walking impossible and can knock a person off their feet. At 300 kilometers per hour, the wind is strong enough to tear buildings apart and hurl cars. At 500 kilometers per hour, we are in the territory of the most extreme tornado winds ever recorded on Earth. Winds capable of throwing entire houses. At 9,000 kilometers per hour, the wind is not a wind in any experiential sense. It is not a force you experience and resist. It is a condition that eliminates the distinction between a solid object and the gas surrounding it, because the gas is arriving at every surface with enough kinetic energy to begin disaggregating it immediately. This is not hyperbole. Kinetic energy scales with the square of velocity. A 9,000 kilometers per hour wind carries roughly 50 times the kinetic energy per unit volume of the most violent tornado wind ever measured on Earth. The atmosphere of HD 189733b at those wind speeds behaves in its effect on solid material less like a fluid flowing past an obstacle and more like an abrasive medium continuously impacting every surface at high velocity. There is no sheltered side, no lee of a rock formation where the wind is calmer. The entire atmosphere is in motion, and the motion is everywhere, at the same speed, in the same relentless way. At those temperatures and those wind speeds, the atmosphere holds suspended silicate particles, the raw material of glass, in fine clouds. On the night side, where the temperature drops by that small 250-degree margin, some of those silicates condense and precipitate. It rains on HD 189733b. It rains silicate glass, not large shards. Tiny particles, roughly a micrometer across, fine glass dust. Under normal conditions, that would be damaging but survivable. Under conditions of wind speeds 7 times the speed of sound, a micrometer of glass becomes a projectile. The glass rain on HD 1897333b does not fall. It scours. It is, physically, an abrasive bombardment moving at supersonic speeds in every direction simultaneously. Any object placed in that environment would be reduced to its constituent atoms in fractions of a second. Not dissolved, not melted, not burned, but literally abraded into nothing by the continuous high-velocity impact of glass particles. And the color of this place? Cobalt blue. In 2013, astronomers used the Hubble Space Telescope to measure the color of HD 189733b directly. Not the color of its star, not an inference, but the actual observed color of the planetary dayside. They measured the slight change in the combined light from the star-planet system as the planet passed behind its star, isolating the reflected light from the planet alone. The planet reflects blue. Not the faded, scattering blue of Earth's sky, but a deep, pure cobalt blue, likely caused by the silicate cloud particles scattering blue wavelengths preferentially in the upper atmosphere. So here is what HD 189733b looks like from space. A cobalt blue sphere, slightly larger than Jupiter, orbiting a dim orange star every 2 days. It looks, at a distance, like the most beautiful planet you have ever seen. Closer, you see the night side, still hot, enough to melt copper, shrouded in supersonic glass dust. Closer still, the atmosphere itself becomes the threat, a continuous planet-wide sandblasting operation running at 7 times the speed of sound, in both directions perpetually. Beautiful, lethal, gorgeous? Wrong. Here is the specific way HD 189733b disturbs your intuitions, beyond the immediate horror of supersonic glass rain. Every feature of this planet is the direct, comprehensible consequence of orbital distance. It is too close. That fact propagates through every aspect of its physics. The tidal locking, the temperature differential, the wind speed, the glass precipitation. Pull it outward to Earth's orbital distance and the whole system relaxes. The wind drops, the temperature falls, the silicates condense and settle, the sky clears. The planet becomes comprehensible, maybe even beautiful in a stable way. But you cannot change the orbital distance. The planet is where it is. The orbit is what it is. The physics simply follows. This is the underlying pattern of every planet in this video. The disturbance is not arbitrary or capricious. It is not a malfunction. It is the physics working correctly, the same equations that govern Earth's atmosphere and weather and geology, applied to conditions that differ from Earth's not in kind, but in degree. The glass rain on HD 189733b is meteorology. The iron rain on WASP 76b is a precipitation cycle. The hot ice on Gliese 436b is thermodynamics. The Roche lobe overflow on WASP 12b is orbital mechanics. The universe is not doing anything unusual. It is doing what it always does, everywhere, all the time. The result is worlds that should not exist by any intuition, built on living inside the narrow band of conditions that Earth provides. HD 189733b established the template. Cobalt blue, supersonic glass, wrong, and this is not the most disturbing planet we will visit today. Chapter 2. The planet where it rains iron. 180 light years from Earth, in the constellation Pisces, orbits a planet called WASP 76b. WASP-76b is a hot Jupiter, a gas giant with roughly Jupiter's mass, orbiting its star every 1.8 Earth days at a distance of about 5 million kilometers. Tidally locked, one face baking in eternal stellar noon, one face in permanent night. The dayside temperature is 2,400 degrees Celsius. Say that slowly. 2,400 degrees Celsius. Iron melts at 1,538 degrees Celsius. The dayside of WASP-76b is almost 900 degrees hotter than the melting point of iron. On the dayside of WASP-76b, iron does not just melt. Iron evaporates. Iron becomes a gas. Iron vapor, atoms of the same element that comprises the core of Earth and the hulls of ships and the hemoglobin in your blood, suspended in an alien atmosphere as a component of the air. The night side of WASP-76b is a different matter. The night side runs at around 1,400 degrees Celsius. Still hot enough to melt iron, but not quite hot enough to maintain it, as vapor at the pressures present in the upper atmosphere. The atmosphere on the dayside, loaded with iron vapor, is driven by the same pressure gradient that drives HD 189733b's winds. The enormous temperature difference between the permanently baked dayside and the merely scalding nightside. It flows at high speed from the dayside to the nightside, and when it arrives on the nightside, the iron cools, it condenses, it precipitates, it rains iron on WASP-76b, liquid iron droplets falling from the sky on the nightside. Iron monsoon, iron weather, a world where the hydrological cycle, the evaporation, transport, condensation, and precipitation cycle that moves water around Earth, has been replaced by an iron cycle, where the iron evaporates in the scorching dayside air, rides the jet stream to the night side, and falls as metallic rain. This is not a speculation or a model output. This was directly observed. In 2020, a team led by David Ehrenreich at the University of Geneva used the espresso spectrograph on the Very Large Telescope to study the atmosphere of WASP-76b during transit, as the planet crossed in front of its star. The key measurement was the Doppler-shifted iron absorption signal from different parts of the planet's limb. On the evening terminator, the boundary where the dayside atmosphere transitions toward the night side, strong iron absorption was detected. On the morning terminator, where the night side atmosphere cycles back toward the dayside, iron absorption was dramatically weaker. The iron is missing from the morning side. The iron that rode the jet stream to the night side has rained out. It is somewhere in the deeper atmosphere, in a condensed layer, falling back toward the lower atmosphere as the planet's fluid interior continues its own chaotic dynamics. And by the time that air cycles back to the dayside, stripped of its iron by the night's weather, it reheats and the cycle begins again. The specifics of what iron rain looks like as a physical phenomenon are genuinely difficult to model, and that difficulty is itself interesting. On Earth, rain forms when water vapor in rising air cools to the dew point, condenses onto aerosol particles, and forms droplets that grow large enough to fall. The condensation nucleus, the microscopic particle around which each droplet forms, is typically a speck of dust, sea salt, or organic material. On WASP-76b, the process is analogous, but the substrate is metal. Iron vapor cooling to the condensation temperature somewhere around 1,800 to 2,000 Kelvin, would nucleate onto available particles and form iron droplets. The size distribution of those droplets, the rate of their growth, the fluid dynamics of their fall through the dense atmosphere, all of these depend on detailed microphysics that existing models only approximate. What we know is that the iron arrives on the day side as vapor, is transported to the night side as vapor, and is detected by its absence on the morning terminator, demonstrating it has condensed and rained out. The exact form it takes as it falls, and what happens when it hits the denser atmosphere below, remains an open research question. A world using a familiar engine to produce an alien outcome. The same physics as terrestrial rain? The working fluid is the same element as the planet's own core. Iron rain, 180 light years away. Still not the most disturbing. Chapter 3. The planet whose atmosphere is hotter than stars. There is a class of planets that challenges one of the most deeply held intuitions about solar systems, that the star is always the hottest thing in it. This intuition is almost always correct. Stars are powered by nuclear fusion, generating energy at their cores and radiating it from their surfaces at temperatures that range from about 2,500 Kelvin for the coolest red dwarfs to 50,000 Kelvin or more for the most massive blue stars. The planets orbiting those stars receive a fraction of that energy, warm themselves by absorbing it, and exist at temperatures determined by how much energy they receive and how much they emit. A planet cannot be hotter than its star because it has no internal energy source, no fusion, no accretion, capable of competing with stellar output. This intuition fails for one extraordinary world. The mechanism that breaks the intuition is worth understanding because it reveals something about the efficiency of stellar irradiation at extreme orbital distances. A planet's temperature is determined by the balance between the energy it absorbs from its star and the energy it radiates away as thermal emission. At any stable temperature, these two rates are equal. The equilibrium temperature of a planet, the temperature at which it radiates away exactly as much energy as it absorbs, scales with the stellar luminosity and the orbital distance in a specific mathematical relationship. Closer to the star means higher absorbed flux, which requires a higher equilibrium temperature to achieve the same radiated flux. For Kelt 9b, the combination of an extraordinarily luminous star, 7,000 times the sun's luminosity, and an extraordinarily close orbit, 3 million kilometers, produces an absorbed flux that is roughly 44,000 times the flux Earth receives from the sun. At that flux, the equilibrium temperature calculation gives day-side temperatures approaching 4,600 Kelvin. No fusion required, no internal energy source. Just a star that is extremely hot and a planet that is extremely close. The surprise is that this number exceeds the surface temperatures of most stars. This is possible because stellar surface temperature is not just a function of stellar luminosity. It is a function of stellar size as well. A very large, luminous but cool star radiates a lot of energy at relatively low surface temperature because of its enormous surface area. A planet at the orbital distance of Kelt 9b is absorbing per unit area of its day side a flux that simply does not exist at the surface of any cool star, because cool stars are too large and spread their luminosity over too great an area. Kelt 9b's situation, extreme luminosity concentrated through a tiny solid angle of sky at 3 million kilometers, is physically different from being on the surface of a cool star. But the temperature result is the same. Kelt 9b orbits a blue-white star called Kelt 9, approximately 670 light-years away in the constellation Cygnus. Called Kelt 9, approximately 670 light-years away in the constellation Cygnus. Kelt 9 itself is an A-type star, hotter, more massive, more luminous than our Sun. Its surface temperature is roughly 10,000 Kelvin. It pours out about 7,000 times more energy than the Sun. It is, by stellar standards, extremely hot. KELT-9b orbits it every 1.48 days at a distance of about 3 million kilometers, tidally locked, day side permanently roasting, night side permanently dark. The day side temperature of Kelt 9b is approximately 4,600 Kelvin. The surface temperature of the Sun is 5,778 Kelvin. Kelt 9b, a planet with no nuclear fusion, no internal energy source beyond the radiation it receives from its star, has a day-side temperature that approaches the surface temperature of the Sun. It is hotter than 80% of all the stars in the Milky Way. It is hotter than every single red dwarf star, the most common type of star in the galaxy, accounting for roughly 70% of all stellar objects. Thousands of stars visible in the night sky have cooler surfaces than the atmosphere of this planet. At 4,600 Kelvin, chemistry stops working, not figuratively, literally. The thermal energy at those temperatures is sufficient to break virtually every molecular bond that exists. Water molecules cannot survive. The oxygen and hydrogen are present but cannot stay bonded. Carbon monoxide, methane, ammonia, carbon dioxide, all dissociated. Even molecular hydrogen, the simplest and most stable diatomic molecule, is partially split into individual hydrogen atoms on the day side. The upper atmosphere of KELT-9b is an atomic gas. Individual atoms of hydrogen, iron, titanium, magnesium, calcium, and other elements, all stripped of their molecular bonds by sheer thermal violence. When astronomers take the spectrum of Kelt 9b's atmosphere during transit, measuring which wavelengths of starlight are absorbed as it passes through the planet's atmospheric limb, they find something that looks nothing like a planetary spectrum. The molecular features that identify a planet's atmospheric composition in every other known exoplanet are largely absent. Instead, the spectrum shows atomic absorption lines: iron, titanium, calcium, barium, magnesium, strontium, elements, not compounds. This is the spectrum of a stellar atmosphere. A cool star. Kelt 9b's atmospheric chemistry is stellar, not planetary. The most fundamental distinction between a planet and a star, that a planet has molecular chemistry while a star has atomic plasma, is erased on Kelt 9b's day side. There is something philosophically destabilizing about this. When astronomers developed the tools to read exoplanet atmospheres, transmission spectroscopy, the measurement of molecular absorption, features during transit, they built a vocabulary based on the assumption that planet atmospheres contain molecules. Water, methane, carbon dioxide, ammonia. These were the expected targets, the features that would identify atmospheric composition and potentially signs of habitability. Kelt 9b does not speak that language. Its atmospheric spectrum reads as stellar, not planetary, because the conditions of its atmosphere are more similar to those found in the photospheres of stars than in the atmospheres of any planet we expected to find. The periodic table above hydrogen and helium, the heavier elements synthesized in stellar nucleosynthesis, is being detected in gaseous form in a planet's atmosphere. Iron, titanium, chromium. These are not atmospheric gases in any planetary framework we developed from studying our solar system. They are stellar tracers, and yet here they are in a planet. The consequences do not stop at chemistry. Kelt 9b is losing its atmosphere at a measurable rate. The upper atmosphere is so hot that hydrogen and helium atoms achieve escape velocity and stream away from the planet continuously. Ultraviolet observations show a comet-like tail of escaping hydrogen gas trailing Kelt 9b in its orbit. The planet is evaporating. At current escape rates, Kelt 9b may have already lost a significant fraction of its original atmospheric mass, and Kelt 9 itself will not live long enough by stellar standards to allow the process to complete naturally. KELT9 is a massive, luminous star that burns through its fuel faster than our Sun. It will exhaust its core hydrogen and expand into a giant star, engulfing the inner system within perhaps 1 billion years. Whether Kelt 9b is completely stripped before then depends on detailed calculations that remain uncertain. But the direction is clear, a planet slowly being reduced to whatever dense remnant lies at its core, surrounded by a galaxy's worth of escaped atmosphere spreading thinly into interstellar space. A planet with a stellar spectrum, a comet tail, a temperature higher than most stars, evaporating in real time 670 light-years away. Not the most disturbing planet. Chapter 4: The Planet Made of Hot Ice. Here is the sentence that should not be possible. It is possible. There is a planet in this galaxy with a surface temperature of 439 degrees Celsius. Its surface, or more precisely, the phase of matter that constitutes its deepest structural layer, is solid ice. Hot, solid ice. Ice that is hundreds of degrees hotter than boiling water, maintained as a solid not by cold, but by pressure. To understand this, you need to understand something that most people do not know about water. Ice is not a single substance. Under different conditions of temperature and pressure, water can form at least 17 distinct crystalline phases, each with a different molecular arrangement, each stable within a different range of conditions. The ice in your freezer is ice, IH, the hexagonal crystal structure that forms at low pressure and low temperature. As pressure increases, ice transitions through a series of other phases: ice 3, ice 5, ice 6, ice 7, each denser than the last. Ice 7 is the relevant phase here. It forms under pressures of roughly 30,000 atmospheres or more, 30,000 times Earth's surface atmospheric pressure. Under those pressures, water molecules are compressed into a cubic crystal structure that is stable at extraordinarily high temperatures. The theoretical stability limit of ice 7 extends to thousands of degrees Celsius at sufficient pressure. Ice 7 at 439 degrees Celsius is not a paradox. It is routine thermodynamics. The planet Gliese 436 Bau is a warm Neptune, a planet about 21 times Earth's mass and 4 times Earth's radius, orbiting a red dwarf star about 33 light-years away. Its orbital period is 2.64 days. At these distances and orbital timescales, you already know what to expect: tidal locking, extreme irradiation, temperatures that should rule out any conventional solid surface. The equilibrium temperature of Gliese 436b is around 649 Kelvin, roughly 376 degrees Celsius. Its measured dayside temperature runs somewhat higher, around 439 degrees. The interior of Gliese 436b is primarily water, not in liquid or gaseous form, but transitioning through pressure phase states with depth. The outer atmosphere is hydrogen and helium. Below that, as pressure increases, water transitions from a supercritical fluid to ice 7, compressed into solidity by the weight of tens of Earth masses of material pressing down from above. At the deepest layers, this solid ice sits at temperatures well above boiling and pressures so extreme that the solid state is forced upon the water molecules simply because the pressure overwhelms the thermal tendency to expand. Hot, solid ice, ice that would cook you, ice that is solid because of weight, not cold. But the ice is not what makes Gliese 436b most disturbing. In 2015, the Hubble Space Telescope observed Gliese 436b during transit and detected something unexpected: a vast, asymmetric cloud of neutral hydrogen surrounding and trailing the planet, stretching more than 50 planetary diameters behind it. The planet has a comet's tail. Gliese 436b, a planet, orbits its star with a comet-like tail of escaping atmospheric hydrogen streaming behind it in its orbit. A ghostly, diffuse shroud of lost atmosphere visible only in ultraviolet light. Red dwarf stars, quieter and dimmer than the sun in visible light, are actually extremely active in the extreme ultraviolet and X-ray range, especially when young. Their energetic radiation strips the outer hydrogen layers from closely orbiting planets in a process called photoionization. The stellar UV energizes hydrogen atoms in the upper atmosphere until they achieve escape velocity and stream away. Gliese 436b is surrounded by a nebula of its own past. The hydrogen trailing behind it is the planet's own atmosphere, ionized and shed, marking the path the planet has traveled in its orbit, like a comet's tail marking its path around the sun. The planet is being unwrapped. Its hydrogen envelope is being stripped layer by layer, exposing the denser, stranger layers below. What is being revealed, as the stripping continues over millions of years, is the Ice 7 interior. The hot solid ice at the heart of this world, surrounded by a ghost of its own lost gases. A planet that is simultaneously solid and 439 degrees, wrapped in escaping gas, trailing its own lost atmosphere through space. Hot ice, comet tail, 33 light years away. There is a specific way in which Gliese 436b is more disturbing than it first appears. And it has to do with what we mean when we say a planet is stable. Planetary stability, the stability of the orbit, the stability of the atmosphere, the stability of the surface conditions, is typically something we take for granted when we think about a world. The Earth has been at roughly its current temperature, and with roughly its current atmospheric composition for hundreds of millions of years. The conditions are stable enough that life has had time to evolve, diversify, and produce organisms capable of studying other planets. Gliese 436b is not stable. It is in a slow-motion catastrophe. The comet tail of escaping hydrogen represents the planet's own future. As hydrogen is stripped layer by layer, the planet changes. Its radius decreases, its density increases. The atmospheric pressure at depth decreases as the total atmospheric mass decreases, changing the phase boundaries of the water below. The pressure that holds the ice 7 solid decreases as material above it is lost. The hot ice, maintained in its impossible state by the weight of everything above, may eventually not have enough above it to stay solid. What Gliese 436b will look like in 1 billion years depends on how fast the stripping continues, how long the star remains active in the UV, and the detailed interior physics that models only approximate. But the direction is established. The planet is losing mass. Its character is changing. The world of hot, solid ice surrounded by escaping gas is a snapshot, a moment in a transformation that began long before any human eye existed to observe it and will continue long after. All of the planets in this video are, in one way or another, in the middle of something. Not in equilibrium, not stable, being transformed by the conditions of their orbits at rates that are fast by geological standards. This is one of the things that makes the universe's exoplanet zoo genuinely disturbing in a quiet way that has nothing to do with glass rain or iron weather. These are not worlds in steady state. They are worlds in process, caught at a specific moment in trajectories that end in stripping, consumption, or transformation. We are watching the universe metabolize its own planetary material, still not the most disturbing planet we will discuss. But we are close. Chapter 5. The planet being consumed. There is a distance from a star that a planet cannot cross without consequences. The Roche limit is the orbital radius inside which tidal forces overcome the self-gravity of an orbiting body. Any sufficiently diffuse body that drifts inside the Roche limit will be torn apart. The part of it closest to the star is pulled harder by the star's gravity than the body's own gravity can hold, and material strips off. The rings of Saturn are the remnants of several objects, moons or captured planetesimals, that drifted inside Saturn's Roche limit and were tidally shredded into the ring system we see today. WASP-12b is a hot Jupiter that has committed the error of drifting too close. WASP-12b orbits a sun-like star about 1,400 light-years away, completing one orbit every 1.09 days. It has a mass about 1.4 times Jupiter. Its orbital distance is roughly 3 million kilometers, inside, or on the inner edge of, its host star's Roche limit. At this distance, the tidal force gradient across WASP-12b's diameter is large enough that the planet cannot maintain a spherical shape. WASP-12b is tidally distorted, stretched into an elongated egg shape, with the long axis pointing towards the star, the near side pulled towards the star's gravity well, and the far side comparatively released. The planet's outer atmosphere is being pulled away. This is called Roche lobe overflow. The Roche lobe is the gravitational boundary around each body in a close binary system, the region in which material is bound to that body. When a planet expands, enough due to heating by its host star, hot Jupiters puff up to larger radii under stellar irradiation to fill its Roche lobe. Material at the outer edge of the lobe is no longer gravitationally bound to the planet. It flows along the boundary and is accreted onto the star. ultraviolet observations of WASP-12b using the Hubble Space Telescope have detected exactly this: a diffuse disk of planetary material orbiting the star inside WASP-12b's orbit. Material stripped from the planet's upper atmosphere, now orbiting the star as a hot, thin accretion disk. The planet is donating its own substance to the star. Not quickly. The estimated mass transfer rate is high enough that WASP-12b will be consumed in roughly 10 million years, a long time by human standards, but an eye blink by stellar timescales. But measurably, detectably, inexorably. Most compellingly, the orbital decay of WASP-12b has been directly measured. Tidal interactions between the planet and the star? Complex. Transfers of angular momentum between the planetary orbit and the star's rotational profile are causing WASP-12b to spiral inward. Each orbit is very slightly shorter than the last. Astronomers have tracked the transit timing of WASP-12b over more than a decade and found that the orbital period is decreasing by about 29 milliseconds per year. That seems tiny. But at this rate, extrapolated forward, WASP-12b will spiral into its star in approximately 3 million years. Let's make the 29 milliseconds feel real, because it is one of the more remarkable measurements in observational planetary science. The orbital period of WASP-12b is 1.09 days, about 94,000 seconds. A decrease of 29 milliseconds per year means the period is shrinking by about 0.03 parts per million per year. To detect that, you need to time the transits. The exact moment WASP-12b crosses its star, with precision of better than a few seconds, and you need observations spanning years to accumulate enough change to measure. This has been done using multiple transit timing datasets spanning from 2008 to the 2020s. Astronomers have accumulated a timing residual, the difference between when transits were expected, if the orbit were stable, and when they actually occurred. That shows a clear accelerating advance. The planet is arriving at transit slightly earlier and earlier with each successive orbit. Not randomly, a smooth, parabolic trend in the timing residuals that is the unmistakable signature of orbital decay. The planet is measurably, quantifiably spiraling in. We can calculate, from the current data, when it will arrive at its star within a range of about 1 million years. 3 million years is not very long. The Earth is 4.5 billion years old. 3 million years ago, our ancestors were Australopithecines, walking upright in East Africa. On that scale, WASP-12b is not just dying, it is nearly already dead. The transit timing record allows us to watch the planet fall into a star in slow motion, measurement by measurement, year by year, 129 millisecond increment at a time. In the transit light curve, the precise dip in stellar brightness as WASP-12b crosses the star, there is a subtle asymmetry. The planet's egg shape means the transit profile is slightly different from that of a spherical planet. The day side, blasted to roughly 2,900 degrees Celsius and puffed outward by that energy, is the first limb to cross the stellar disk. The tidally stretched, leading and trailing edges of the planet distort the transit shape in ways that can be measured with precision photometry. A world the size of Jupiter stretched into an egg by tidal forces, losing its atmosphere to the star it orbits, spiraling inevitably inward toward being consumed entirely, while astronomers 1,400 light-years away track its death in 29 millisecond increments. Deeply disturbing. Not the most disturbing planet in the known universe. Chapter 6. The planet that eats light there is a number that defines how visible an object is. It's albedo. Albedo is the fraction of incident light that an object reflects. An albedo of 1 means perfect reflectivity, every photon bouncing back, nothing absorbed. An albedo of 0 means perfect absorption, every photon consumed, nothing returned. Real objects fall somewhere between. Earth has an albedo of about 0.30. It reflects 30% of the sunlight that hits it. The moon is darker, around 0.12. Fresh snow reaches about 0.80. Vantablack, the engineered carbon nanotube material that holds records as the darkest human-made substance, absorbs about 99.965% of visible light, an albedo of roughly 0.00035. TRES-2b is a hot Jupiter orbiting a Sun-like star about 750 light-years away. Its orbital period is 2.47 days. Its dayside temperature is around 1,000 degrees Celsius. By hot Jupiter standards, these numbers are moderate, not the hottest, not the fastest. Its albedo has been measured at less than 0.01, less than 1% reflected, more than 99% absorbed. TRES-2b is darker than Vantablack. It is darker than coal. Coal has an albedo of around 0.04, 4 times more reflective than TRES-2b. It is darker than any natural material found anywhere on Earth. It is, as far as we can measure, the darkest planetary body ever discovered. The question of why is not fully resolved. Hot Jupiters at around 1,000 degrees Celsius are expected to lack the reflective cloud layers that give cooler gas giants their high albedos. Water ice clouds and ammonia clouds evaporate at those temperatures. Without clouds, the upper atmosphere is a clear gas, and gases absorb more efficiently than they reflect. Additionally, sodium and potassium vapor, alkali metals that are present in hot atmospheres, absorb visible light strongly, reducing reflectivity further. Some models also implicate titanium oxide in the opacity. But even models that include all of these effects struggle to get the albedo as low as measured. TRES-2b is darker than theory comfortably predicts. Something in its atmosphere is absorbing light with extraordinary efficiency. Some combination of absorbers, possibly including unknown or poorly characterized atmospheric species, that together consume almost every photon that arrives. It is worth pausing on how this albedo was actually measured, because the measurement technique itself is striking. You cannot point a telescope at TRES-2b and photograph its color the way you might photograph a planet in our solar system. At 750 light-years, the planet is far too close to its star in angular terms to be resolved separately. Instead, the albedo is determined by secondary eclipse photometry, the same technique used to determine the color of HD 189733b. As the planet passes behind the star during each orbit, the combined light from the star-planet system drops by a tiny amount, the fraction corresponding to the reflected light from the day side of the planet. By measuring this drop in visible wavelengths very precisely, the fraction of light being reflected can be calculated. For Tauri S2b, that drop is so small that it is essentially undetectable in visible light. The planet contributes so little reflected light to the combined system flux that removing it from the measurement, hiding it behind the star, causes essentially no change. The secondary eclipse in visible light is absent, statistically indistinguishable from zero. The planet was declared darker than any known body, not because someone measured a specific albedo value directly, but because the expected reflected light signal was so small, it fell below measurement thresholds. The fact that we know Tauri 2b is dark at all is a consequence of the precision of the Kepler Space Telescope's photometry. Kepler could measure stellar brightness with a precision of parts per million. And even with that precision, TRES 2b's reflected light contribution was at the very edge of a detection. The albedo upper limit of 0.01 is exactly that, an upper limit derived from the absence of a detectable secondary eclipse signal in visible light, combined with constraints from thermal emission at infrared wavelengths. An unknown absorber, undetectable in reflected light, darker than engineered materials. The science of why Tauri S2b is so dark remains genuinely open, and that openness, the fact that our models of hot Jupiter atmospheres cannot yet account for an object this dark, is itself a form of disturbance. The universe has produced something our best theories underpredict. Consider what Tauri S2b's albedo means for its energy balance. When a planet absorbs more than 99% of the light hitting it, the energy has to go somewhere. In a simplified planetary energy budget, a planet absorbs stellar radiation and re-emits it as thermal infrared radiation until equilibrium is reached. The emitted infrared balances the absorbed stellar energy. For Tauri S2b, the full absorption is so efficient that virtually all of the incoming stellar energy is converted to heat in the atmosphere. This drives the atmospheric dynamics, the circulation, the jet streams, the heat redistribution between the day side and night side. Tauri S2b's extreme absorption is the engine behind its atmospheric behavior. Invisible light, the kind your eyes are sensitive to, Tauri S2b is nearly invisible. If you could stand far enough away to see both it and its star in the same field of view, the star would be a bright point, and Tauri S2b, a Jupiter-sized planet orbiting at 4.9 million kilometers from it, would be so dark as to be effectively invisible except as an absence, a slight darkening of the star's light as the planet transits. It would not gleam. It would not glow with reflected starlight. It would absorb the starlight and return heat, silently, continuously, in a one-way transaction with its own sun. What does it look like from the day side? Probably not much. Phew, star, enormous and bright, filling much of the sky at 4.9 million kilometers. And surrounding you, in every direction, an atmosphere that is swallowing light. You would not see a sky, you would see an absence. A black where sky should be, converting incoming photons to thermal energy with mechanical efficiency, emitting only in the infrared. Wavelengths your eyes cannot detect. A world that eats light. A Jupiter-sized black hole in the sky, 750 light-years away, silently consuming the output of its star. Still not the most disturbing. Chapter 7. Setting the Stage. Let's take stock. In 6 chapters, we have encountered worlds that should stretch your intuition about what planets are allowed to be. cobalt blue world whose glass rain would sand you to atoms in milliseconds. A world with iron weather. A world whose atmosphere is chemically stellar. A world of hot ice slowly losing its ghostly hydrogen tail. A world being stretched into an egg shape and consumed by its star one, 29 millisecond orbit at a time. A world darker than any engineered material, converting starlight to heat without return. Each of these planets is disturbing in a legible, describable way. You can point to the specific physical parameter that makes them extreme. The orbital distance, the temperature, the tidal force, the albedo. The disturbance is at the end of a known axis. Turn the dial far enough in one direction and you get something alarming, but the dial itself is familiar. There is another thing that all of these planets share, one that matters more than you might expect. They are all gas giants or near gas giants. HD 189733b, gas giant. WASP 76b, gas giant. KELT 9b, gas giant. Gliese 436b, a mini Neptune with a deep fluid interior. WASP 12b, gas giant. TRES 2b, gas giant. Every planet so far in this video is an enormous ball of gas or fluid, lacking anything that could reasonably be called a solid surface. This matters because the concept of a surface is where liquid water can pool, where things where liquid water can pool, where things exist at a specific location. Gas giants do not have this. They transition gradually from gas to fluid to denser fluid as depth increases, with no clean boundary. The disturbance of these planets is real and extreme, but it is the disturbance of an environment, not a world. 55 Cancri is a rocky planet. In any other orbit, in any other star system, a planet of its mass and composition would have a surface, a crust, solid ground. It is in this orbit. And the result is that the ground is not ground. The planet we are about to discuss is disturbing for a different reason. Its disturbance does not come from a single extreme parameter. It comes from a specific combination of physical conditions that produce an environment where the concept of a planetary surface, the idea of a place, a ground, somewhere that things exist in a stable state, becomes not just hostile, but meaningless. A world where the surface is a global ocean of liquid rock that has never solidified, where the atmosphere is vaporized mineral, where the day-night boundary is not between hot and cold, but between molten and slightly less molten. Where the most fundamental question you can ask about a planet, what is the ground like, has an answer that restructures what the word ground even means. The planet is 55 Cancri e. It orbits the star 55 Cancri, also called Copernicus, about 41 light-years from Earth. It was discovered in 2004. It has a mass about 8 times Earth's and a radius about twice Earth's. It orbits its star every 17.7 hours. Not days, hours. 1 year on 55 Cancri e is 17.7 hours long. It orbits its star at a distance of 2.3 million kilometers. Closer than any planet in this video except the most extreme hot Jupiters, but more disturbing than any of them, for reasons that have nothing to do with the temperature and everything to do with what the temperature does to rock. Because 55 Cancri e is a rocky planet, not a gas giant, not a mini Neptune with a deep fluid interior, a rocky planet, a terrestrial world, something that, in a different orbit around a different star, might look a great deal like Earth. This matters enormously. Everything we have seen so far, the cobalt blue world, The iron rain, the stellar atmosphere, the hot ice, the consumed giant, the light-devouring darkness, all of those are gas giants or mini-Neptunes. Enormous objects made primarily of hydrogen and helium or deep fluid water. Objects that have no solid ground by definition. Objects where the question, "What is the surface like?" is already somewhat ill-formed because they do not have surfaces in the way Earth has a surface. 55 Cancri is a rocky planet. It is made of rock and metal. It has, or should have, a surface. It should have a ground, a crust, a place where solid matter meets whatever lies above it. It does not look anything like Earth. The surface temperature on the day side of 55 Cancri has been measured at approximately 2,700 degrees Celsius. The night side runs at around 1,300 degrees Celsius. At 2,700 degrees, rock does not just heat up. Rock melts. Not certain rocks, not certain minerals. Rock. The melting point of granite is around 700 to 900 degrees Celsius. The melting point of basalt, the most common volcanic rock, is around 1,100 to 1,250 degrees. The melting point of peridotite, the rock that makes up Earth's upper mantle, is around 1,300 degrees. Every type of rock that makes up Earth's crust and mantle melts at temperatures well below 2,700 degrees Celsius. The surface of 55 Cancri is not solid. It cannot be. The physics does not allow it. Every rock-forming mineral, every silicate, every oxide, everything that would constitute a planetary crust, all of it is liquid at the day side. Temperature. The surface of 55 Cancri is a global ocean of liquid rock, magma, not volcanic regions, not lava flows, not a hot spot in the crust. The entire dayside surface, an ocean of molten rock, a magma world with no solid ground anywhere, possibly extending around the whole planet, possibly kilometers deep, churning under an atmosphere that, as we will see in Part 2, should not exist at all. Chapter 8, 55, Cancri, the world that should not be a world. 41 light years from Earth, in the constellation Cancer, orbits a star called 55 Cancri. 55 Cancri is a binary star system, two stars gravitationally bound to each other, orbiting their common center of mass. The primary star, 55 Cancri is a G-type star, slightly smaller and slightly cooler than the Sun, but close enough in character that if you swapped our Sun for 55 Cancri, the differences would be subtle. It is old, about 10.2 billion years, more than twice the age of our solar system. It has been burning hydrogen in its core for longer than the Earth has existed, longer than complex life has existed, longer than most of the geological record we can read. 55 Cancri has 5 known planets. This is a significant number. Multi-planet systems are common in the exoplanet census, but 5 confirmed planets around a single star is enough to call it a system in the full sense. A family of worlds with distinct orbits, distinct characters, distinct histories. The outermost known planet, 55 Cancri d, is a gas giant orbiting at a distance roughly comparable to Jupiter's distance from our Sun. There are intermediate planets at various distances. The architecture of the 55 Cancri system is in some ways reminiscent of our own solar system, with a mix of inner and outer worlds and a broad range of orbital configurations. And then there is 55 Cancri. 55 Cancri orbits the primary star at a distance of approximately 2.3 million kilometers. Mercury, closest planet to our Sun, orbits at 58 million kilometers. 55 Cancri E is 25 times closer to its star than Mercury is to ours. Its orbital period is 17.7 hours. In the time it takes you to sleep, wake up, eat, and commute to work twice, 55 Cancri E has completed a full year. It was first detected in 2004 using the radial velocity method, measuring the tiny Doppler wobble its gravity induces in the host star's spectrum. It was confirmed and characterized further by transit observations. It crosses the face of 55 Cancri A once every 17.7 hours, causing a tiny, repeating dip in the star's brightness. From those transit measurements, its radius was determined approximately 1.875 times the radius of Earth. From the radial velocity data, its mass was established at roughly 8 times Earth's mass. These two numbers, radius and mass, allow the calculation of density, and density constrains composition. The density of 55 Cancri E comes out at approximately 6.7 grams per cubic centimeter. Earth's average density is about 5.5 grams per cubic centimeter. The Moon's is about 3.3, Iron's is about 7.9. The density of 55 Cancri E is intermediate between Earth's overall density and the density of pure iron, consistent with a planet that is predominantly rocky, like Earth, Venus, and Mars, but with a higher proportion of iron and denser silicate minerals. The density argument is important because it closes off alternative explanations. A planet with a deep hydrogen and helium envelope, a sub-Neptune, a gas-rich world, would have a much lower density, typically below 3 or 4 grams per cubic centimeter. A planet with a large water ice layer, an ocean world, or a water super-Earth would also be less dense, because water's density is 1 gram per cubic centimeter, and a thick water layer would pull the bulk density toward that value. The density of 55 Cancri E rules out substantial hydrogen, helium, or water envelopes. The planet is, within the constraints of the measurement uncertainties, a bare, rocky body, iron and silicate, compressed to high density by its own mass, but not enriched in low-density volatiles. There was a period, in the early years of 55 Cancri E's study, when some researchers proposed that the planet might be a diamond world, that the high pressures in its interior, combined with the carbon-rich stellar composition of 55 Cancri A, might have produced a planet in which carbon had crystallized as diamond rather than graphite, making the interior of the planet partially composed of diamond at high pressure. This model was discussed seriously for several years and generated considerable public attention. Subsequent analysis of the star's actual carbon-to-oxygen ratio, a key determinant of whether a planet's interior would be carbon-rich or silicate-rich, suggested that 55 Cancri A is not as carbon-enriched as the diamond world model required, and the hypothesis has largely been set aside. 55 Cancri E is almost certainly a conventional, silicate iron rocky planet, just one that happens to be sitting at 2.3 million kilometers from its star. This is, without ambiguity, a rocky planet, a super-Earth, larger and more massive than Earth, but in the same broad class of terrestrial worlds, made of the same materials as Earth, silicate rock, iron, magnesium oxides, calcium, aluminium. The periodic table of rock, not a gas giant with a fluid interior, not an ice giant with a deep water layer, a rock, a world made of stone, at 2.3 million kilometers from its star. And this is where the concept of a rocky planet starts to break down. Chapter 9, the surface that cannot exist. The dayside temperature of 55 Cancri A has been measured by multiple independent observations. The Spitzer Space Telescope made infrared measurements that constrained it. The Cheops mission refined it. The James Webb Space Telescope, since its science operations began in 2022, has observed 55 Cancri E in extraordinary detail and produced the most precise characterization of its thermal properties yet published. The dayside temperature is approximately 2,700 degrees Celsius. Let's build this number carefully, because understanding what 2,700 degrees Celsius does to rock is essential to understanding why 55 Cancri E is the most disturbing planet in the known universe. The melting point of granite, the most common continental rock on Earth's surface, the rock that makes up most of the world's mountain ranges and continental interiors, is approximately 700 to 900 degrees Celsius, depending on composition and pressure. At 1,200 degrees Celsius, most granitic rocks are fully liquid. The melting point of basalt, the volcanic rock that makes up the ocean floors and the surfaces of Venus, Mars, the Moon, and most rocky bodies in the solar system, is approximately 1,100 to 1,250 degrees Celsius. Above 1,300 degrees, virtually every basaltic and granitic rock that constitutes a planet's crust is molten. The melting point of peridotite, the iron and magnesium-rich silicate rock that constitutes Earth's upper mantle, the layer below the crust, is approximately 1,300 degrees Celsius at the surface and higher at depth due to the pressure. If you could bring a chunk of Earth's mantle to the surface and let the pressure off, it would melt at about 1,300 degrees. The melting point of iron, the metal that constitutes the core of every rocky planet, the densest and most refractory common planetary material, is 1,538 degrees Celsius. 55 Cancri E's dayside temperature is 2,700 degrees Celsius. This exceeds the melting point of granite by 1,800 degrees. It exceeds the melting point of basalt by 1,450 degrees. It exceeds the melting point of peridotite by 1,400 degrees. It exceeds the melting point of iron by more than 1,100 degrees. At 2,700 degrees Celsius, there is no solid planetary material, not the crust, not the upper mantle, not the core material. Every rock-forming mineral, every silicate, compound, every oxide, every metal that could constitute a planetary surface is liquid at the dayside temperature of 55 Cancri E. And not just barely liquid, liquid by a margin of hundreds to over 1,000 degrees. The dayside surface is not on the edge of melting. It is so far into the melt regime that it is approaching the temperatures at which some rock-forming materials begin to vaporize. The boiling point of silicon dioxide, the most abundant compound in Earth's crust, is approximately 2,230 degrees Celsius. The boiling point of magnesium oxide, The dominant compound in Earth's mantle is approximately 3,600 degrees Celsius. The boiling point of iron, the planetary core material, is approximately 2,862 degrees Celsius. The day side of 55 Cancri E at 2,700 degrees is above the boiling point of silicon dioxide. Parts of the surface are approaching the boiling point of iron. The day side of this rocky planet is not just covered in liquid rock. Parts of it are in the process of transitioning from liquid to gas. The surface minerals are evaporating into the atmosphere. This is not a volcanic world in the way that Io, Jupiter's moon, the most volcanically active body in the solar system, is volcanic. Io has a surface. It has solid ground. The volcanoes on Io erupt from cracks in that solid surface, depositing molten material that cools and solidifies in the cold of the outer solar system. The volcanoes are disruptions of a stable, solid surface. 55 Cancri E has no stable solid surface. The entire day side is a global ocean of liquid rock, a magma ocean, with no solid land anywhere. It is not a planet with a surface that occasionally melts. It is a planet whose surface is the melt. The concept of ground, the thing you stand on, the thing that makes a rocky planet a place, has been replaced by a fluid at temperatures approaching the boiling point of rock. What does this magma ocean look like? On Earth, lava flows from volcanic eruptions are viscous, slow-moving, and visually spectacular. Red-orange glowing fluid moving at walk-in pace, or slower, solidifying at the edges as it contacts the cooler air. The lava ocean of 55 Cancri E is not like this. At 2,700 degrees, silicate melts are significantly less viscous than Earth temperature basaltic lava. They flow more freely, more like a very hot liquid than a thick paste. The dayside ocean is a churning, convecting fluid, driven by the continuous energy input from the star above, with hot material rising, spreading, and sinking in circulation cells, driven by the enormous thermal gradient between the star-facing surface and the deeper, somewhat cooler interior. The surface of this ocean glows, not just in infrared, invisible light. At 2,700 degrees, a black-body radiator emits light across the visible spectrum, with peak emission in the yellow-orange range, and significant emission even in the blue. The day side of 55 Cancri E glows visibly like a coal in a fire from the heat of the liquid rock itself. The planet is self-luminous. It doesn't need its star to be visible. The surface of the magma ocean radiates enough visible light to glow in the dark of space from the thermal energy alone. This is what was detected by the James Webb Space Telescope: thermal emission from the planet's dayside surface, far in excess of what reflected starlight alone would produce. The surface of this ocean glows, not just in infrared, invisible light. At 2,700 degrees, a black-body radiator emits light across the visible spectrum, with peak emission in the yellow-orange range and significant emission even at blue wavelengths. The day side of 55 Cancri E glows visibly like a coal in a fire, but enormously more intense from the thermal energy of the liquid rock itself. The planet is self-luminous. It does not need starlight to be bright. The magma ocean radiates enough visible light from its own thermal energy that the planet would glow in the dark of space without any star nearby. This is not metaphorical. the thermal emission of a 2,700-degree surface radiates significant power across visible wavelengths. For comparison, the filament of an incandescent light bulb operates at around 2,500 to 3,000 Kelvin, roughly the same temperature range as the day side of 55 Cancri E, and glows yellow-white, producing visible light from thermal emission alone. The magma ocean of 55 Cancri E is, across its entire dayside surface, at incandescent filament temperatures. Every square meter of the magma ocean surface is emitting visible light like a hot element in a lamp. And the dayside surface is not a few square centimeters of tungsten wire. It is a hemisphere of a planet with 3.5 times Earth's radius, a surface area far larger than Earth's entire land and ocean combined. The total luminosity of 55 Cancri E's thermal emission is a tiny fraction of its star's output, but it is genuinely measurable. The James Webb Space Telescope was designed to detect exactly this kind of emission, the faint thermal glow of a small, hot body against the background of a far brighter star. By timing secondary eclipses, the moments when the planet passes behind the star and its thermal emission is hidden, and comparing the total system brightness with and without the planet's contribution, JWST can measure the planet's dayside emission directly. This is the measurement that revealed both the existence of the atmosphere through the elevated nightside temperature and the variability through changes in the dayside emission between different observing epochs. We are, in a real and literal sense, detecting the glow of a lava ocean 41 light-years away, not imaging the surface, not resolving any detail, just the total integrated thermal emission from a hemisphere of liquid rock, red-shifted by 41 light-years of travel, arriving as a measurable flux in the mid-infrared detectors of James Webb. A glowing ocean of liquid rock, kilometers deep, covering the entire dayside, with no solid ground anywhere. Chapter 10. The Atmosphere of Vaporized Stone. Here is where 55 Cancri E stops being merely extreme and becomes genuinely, structurally disturbing. Every planet that has retained an atmosphere has one because of a specific physical and chemical process. Volatile compounds, materials that exist as gases or low-temperature liquids under planetary surface conditions, were delivered to the planet during formation, and if the planet's gravity was sufficient and its temperature low enough, were retained as an atmospheric layer. Earth's atmosphere is nitrogen, oxygen, argon, water vapor, and carbon dioxide. All compounds that are gases at Earth's surface, temperatures, and pressures. Mars lost most of its atmosphere because its gravity was too weak and it lost its magnetic field, allowing the solar wind to strip it away. Venus has a thick CO2 atmosphere because CO2 degassed from its volcanic interior. The atmospheres of planets are made of things that are naturally gaseous at the temperatures where those planets exist. 55 Cancri E's temperatures rule out all of those conventional atmospheric components. Water vapor, nitrogen, carbon dioxide, methane. All of these molecules are chemically dissociated at the temperatures of 55 Cancri E's dayside. The thermal energy is sufficient to break molecular bonds. At 2,700 degrees, even relatively stable inorganic compounds break down. So by conventional logic, 55 Cancri E should have no atmosphere. It is a rocky planet with surface temperatures too high, for any conventional volatile compound to form stable molecules. The solar wind from its nearby star is energetic and continuous. The planet is tidally locked, so the day side is permanently exposed to this bombardment. On first principles, you would predict a bare, rocky surface with no atmospheric pressure worth measuring. In 2024, the James Webb Space Telescope published observations of 55 Cancri L that overturned this prediction completely and produced the most astonishing result in the study of rocky exoplanet atmospheres yet reported. The publication, by a team led by Ren Yu Hu at NASA's Jet Propulsion Laboratory, used JWST's MIRI instrument, the mid-infrared instrument, sensitive to thermal emission in the mid-infrared wavelengths where hot planetary surfaces glow most brightly, to measure 55 Cancri E's thermal phase curve. A phase curve is a measurement of the planet's total infrared emission as a function of orbital phase. From when the day side faces us, through the full 17.7-hour orbit, to when the night side faces us and back again, in a 17.7-hour orbit, a single continuous observation lasting a day and a half can capture the full phase curve, watching the planet rotate through its entire orbital cycle relative to our line of sight. The key measurement in a phase curve is the temperature contrast between the day side and night side. For a planet with no atmosphere, a bare rock, the day side temperature reflects the direct stellar irradiation, and the night side temperature is determined only by the planet's own interior heat, with essentially no connection between the two. The result for a bare rock is a very large day-night temperature contrast, day side blazing hot, night side extremely cold. For a planet with an atmosphere, heat is transported from the day side to the night side by atmospheric circulation, and the night side is warmer than it would be for a bare rock. The JWST phase curve of 55 Cancri E showed a night side temperature substantially warmer than the bare rock prediction. The heat was being transported. An atmosphere was present, thick enough and dynamic enough to carry a meaningful fraction of the day side's thermal energy to the permanently shaded night side and deposit it there, raising the night side temperature by hundreds of degrees above what a bare rock would produce. 55 Cancri E has an wide atmosphere, not a thin trace atmosphere, a substantial atmosphere, thick enough to redistribute heat from the day side to the night side, thick enough to produce an observable thermal signature, thick enough that it changes the planet's energy budget in a measurable way. The JWST observations measured the thermal emission from the planet's day side and night side separately, using secondary eclipse observations and phase curve data. If 55 Cancri E had no atmosphere, the day side would be at maximum temperature and the night side would be extremely cold, essentially at the temperature of deep space on the permanently shadowed face. Instead, the night side temperature is substantially elevated above what it would be for a bare rock. Warm enough that heat is clearly being transported from the day side to the night side through some medium. That medium is the atmosphere. But what kind of atmosphere can exist at 2,700 degrees on the day side of a rocky planet? The answer, once you work through the physics, is the only thing that can exist at those temperatures, and that comes from a rocky planet. The atmosphere is vaporized rock, mineral vapor, the gases produced when rock boils. At temperatures above 2,200 to 2,700 degrees, silicon dioxide, magnesium oxide, iron oxide, calcium oxide, and the other mineral compounds that constitute rock begin to contribute measurably to the gas phase above the magma surface, a process called vapor pressure, where even at temperatures below the boiling point, some molecules escape from the liquid surface into the gas above. Above the boiling points of specific minerals, the vapor pressure becomes the dominant pressure, and a true atmospheric component of that mineral exists. At 55 Cancri E's dayside temperatures, this vapor pressure atmosphere is substantial. The atmosphere of 55 Cancri E is, in all likelihood, a mixture of silicon monoxide, gas, sodium vapor, potassium vapor, oxygen, and other vaporized mineral components. This is sometimes called a mineral atmosphere or a rock vapor atmosphere, terms that have no analog in any solar system body, terms that atmospheric scientists had to develop specifically to model planets like 55 Cancri E because no prior framework existed for them. The distribution of this atmosphere is profoundly asymmetric. On the day side, where temperatures are 2,700 degrees, the magma ocean continuously evaporates, feeding new material into the vapor atmosphere. The vapor is carried by atmospheric circulation toward the terminator, the day-night boundary, and then toward the night side. On the night side, where temperatures are dramatically lower, still hot by Earth standards, around 1,300 degrees in the JWST measurements, some of the mineral vapor condenses. Silicon dioxide solidifies. Magnesium oxide solidifies. The minerals rain out on the night side in a process that is, in its fundamental structure, exactly the same as the iron rain on WASP 76b or the silicate glass rain on HD 189733b, but the material is the ground itself. The night side of 55 Cancri E receives a constant, slow deposition of condensed rock from the atmosphere. Mineral compounds that evaporated off the dayside magma ocean are carried overhead by atmospheric circulation and freeze out on the night side, gradually building up a layer of condensed rock minerals. The cycle is complete. The ground evaporates. The sky becomes rock vapor. The rock vapor condenses on the other side. The condensed rock, if it can accumulate and cool sufficiently, would form a new solid surface on the night side. The entire planet's geology is running as an atmospheric cycle. Think about this carefully, because it is genuinely without analog in human experience. On Earth, the geological processes that move rock material, volcanism, erosion, subduction, uplift, operate on timescales of millions to hundreds of millions of years. The rock that makes up a mountain range today was ocean sediment hundreds of millions of years ago and will be recycled into the mantle and re-erupted as new volcanic rock hundreds of millions of years from now. The geological cycle is vast, slow, and driven by the enormous thermal engine of Earth's interior. On 55 Cancri E, the geological cycle runs through the atmosphere. The magma ocean on the day side evaporates minerals that travel through the air to the night side and deposit as solid rock. The solid rock on the night side, if it ever reaches sufficient depth and accumulates enough mass, will eventually be remixed toward the day side as the global convection of the planet redistributes material. The geological timescale on 55 Cancri A is not millions of years. It is the atmospheric circulation timescale, probably days, possibly weeks. 55 Cancri E's geology is a weather cycle. The rock moves through the sky. Chapter 11, The Light That Should Not Flicker. In 2023 and 2024, observations of 55 Cancri E by the James Webb Space Telescope produced a result so unexpected that it prompted significant discussion about what the planet's atmosphere actually is and what is happening on its surface. The planet's brightness changed, not its brightness during transit, the expected dimming as it crosses the star, not a one-time variation that could be attributed to instrument noise. The brightness of the planet's thermal emission, the infrared glow from its hot day side, changed between observations taken at different times, significantly. The dayside temperature, as measured from the thermal emission, varied by hundreds of degrees between different epochs of observation. This should not happen. A tidally locked planet orbiting its star at a fixed distance with a stable atmosphere should have a stable dayside temperature. The energy input from the star is constant. The atmospheric structure should reach a steady state. The thermal emission should be reproducible. 55 Cancri E's thermal emission is not reproducible. It varies. The planet's dayside temperature shifts significantly between observations, suggesting that the planet itself, the surface and atmosphere system, is not in a steady state. Something is changing. What could cause this? The current leading hypothesis is that 55 Cancri E's atmosphere is not static. The mineral vapor atmosphere is dynamic. Its structure, density, and circulation change over time in ways that affect how efficiently heat is transported from the day side to the night side, and how the thermal emission profile looks from outside. The atmosphere may partially collapse. When temperatures fluctuate slightly, the vapor pressure of the mineral components can change significantly, causing the atmospheric density to vary. A thicker atmosphere redistributes heat more efficiently, a thinner one less so. The dayside temperature changes accordingly. But there is a more dramatic possibility that cannot yet be ruled out, and it is the most unsettling interpretation of the variability data. The magma ocean itself may be variable, not in the sense of varying in temperature smoothly, but in the sense of having large-scale surface structure that changes. Volcanic activity from the depths of the planet's interior could periodically disturb the surface of the magma ocean, releasing plumes of gas and particulates that temporarily alter the atmospheric opacity and change the observed thermal emission. Large-scale convection cells in the magma ocean could change their orientation or intensity over time, shifting the location of the hottest regions on the day side. Some models have even proposed that 55 Cancri E's surface may be partially solidified in some regions and liquid in others, with the boundary between solid and liquid shifting dynamically as the internal heat distribution changes. A planet where some regions have a solid crust floating on the underlying magma ocean, not unlike the way ice floats on a polar ocean on Earth, but where the crust is not permanent, forming in regions where conditions allow and melting back, again as the underlying magma churns. A surface that solidifies and melts, that forms a crust and loses it. A geology that is not slow and stable, but fast and chaotic, with the entire character of the surface, liquid or solid, thin crust or open magma, potentially shifting over timescales of years. The variability data is not yet conclusively explained. The JWST observations have established that the variability is real. It is not instrumental noise. It reproduces across multiple independent datasets, and it implies changes in the dayside thermal structure of the planet over timescales of months to years. The explanation remains an open scientific question about a planet 41 light-years away that is actively, observably, measurably doing something we do not understand. A world that is not only extreme in its conditions, but is surprising us with new behavior even as we observe it. The variability of 55 Cancri A invites comparison with something familiar from geology: the behavior of volcanic calderas on Earth. Calderas like Yellowstone, Campi Flegrei, and Tal do not erupt continuously. They cycle through periods of inflation, activity, and relative quiescence as magma moves in and out of subsurface chambers, as hydrothermal fluids redistribute, as the pressure and temperature at depth fluctuate. From above, even without an eruption, the surface of a caldera region shows subtle changes in temperature, ground deformation, and gas emission that reflect the dynamics below. 55 Cancri E may be doing something analogous, but across the entire surface of the planet, at temperatures far exceeding anything Earth's calderas reach. The magma ocean is not a static pool. It is a convecting fluid, with hot material rising from depth, spreading across the surface, cooling slightly at the top, and sinking again in circulation cells driven by the planet's internal heat and the thermal gradient imposed by the star above. These convection cells do not have fixed positions. They migrate, merge, split, and reorganize over time, shifting the distribution of the hottest regions on the dayside surface. When the convection pattern shifts, the effective emission temperature of the dayside changes. More hot material rising in one region increases the emission from that region. A large convection cell that moves its upwelling region toward the limb of the planet, the edge of the dayside as seen from Earth, changes the thermal emission profile in a way that the JWST instruments can detect as a shift in the measured dayside temperature. We are, in other words, possibly watching the convection of a global magma ocean from 41 light-years away, not directly imaging it. The planet is far too small and far too close to its star for any direct imaging, but detecting its signature in the thermal emission as the shifting of the hot zones on the surface changes the planet's overall glow. If this interpretation is correct, then JWST is giving us something unprecedented. Real-time data on the interior dynamics of an alien lava world. Not its static properties, but its behavior over time. The planet is not just an extreme object. It is a dynamic system, actively changing, revealing its interior processes through the fluctuations in its thermal emission. An open scientific question about a planet 41 light-years away that is actively, observably, measurably doing something we do not understand. A world that is not only extreme in its conditions, but is surprising us with new behavior, even as we observe it. Chapter 12. Why this is the most disturbing planet in the universe. We have visited 6 worlds so far, each one extreme in a specific and describable way. Now we have visited 55 Cancri E in detail. Let me make the case for why it earns the title of most disturbing planet in the known universe. And why, that title is not merely rhetorical. Every other planet in this video is disturbing because of what it does to matter that arrives in its environment. HD 189733b destroys things with glass. WASP 76b processes iron as weather. Kelt 9b dissolves molecules with heat. Gliese 436b compresses water into exotic solid phases. WASP 12b consumes planetary mass through tidal overflow. TARIS 2b consumes photons. In each case, the disturbance is what happens to other things, to atmospheric particles, to iron vapor, to hydrogen molecules, to starlight, in the presence of the planet's extreme conditions. 55 Cancri E is disturbing because of what it does to itself. The disturbance of 55 Cancri E is not an environmental condition imposed on other matter. It is what happens when a rocky planet, an object whose defining physical character is that it has a solid surface, a crust, a place, is subjected to conditions that eliminate the possibility of that defining character. 55 Cancri E is a rock that cannot be a rock, a world that cannot be a world. The conditions of its orbit have taken everything that makes a rocky planet what it is: the crust, the geology, the surface, and unmade it. The crust has melted into a global ocean. The ground has become weather cycling through the atmosphere. The geology runs on time scales of days. The surface temperature is above the boiling point of several major rock-forming minerals. The atmosphere is made of the vaporized body of the planet itself. And on top of all of this, the planet's behavior is variable. It changes observably and unexplainedly in ways that we do not yet understand. Other disturbing planets are disturbing because they are extreme versions of recognizable types. HD 189733b is an extreme gas giant atmosphere. WASP 76b has an extreme precipitation cycle. Kelt 9b is an extremely hot gas giant. The template is familiar, the values are alarming. 55 Cancri E is not an extreme version of a familiar type. It is a familiar type, a rocky planet, the type of planet that includes Earth, Venus, Mars, Mercury, operating in conditions where the defining features of that type are erased. It is the same category as Earth, run through conditions that remove everything that makes Earth a place. This is why it is more disturbing than the others, in a specific and precise way. The others disturb by being extreme. 55 Cancri E disturbs by being familiar and wrong simultaneously. It is a rocky planet. It should have ground. It should have geology. It should have a surface that accumulates material over time, that builds mountains and valleys and plates and oceans. A surface that is the foundation of everything a planet is as a place. The ground is a global ocean of liquid rock at temperatures approaching the boiling point of stone. The geology is a weather system. The surface is either magma or rock vapor or condensed mineral rain, depending on which hemisphere you are on and what the current atmospheric conditions are. And 41 light years away, it is glowing, visibly. The infrared telescopes of JWST can see its thermal emission directly. They can watch its dayside temperature vary, month by month, as whatever is happening on and above the magma ocean changes the planet's energy distribution. We are watching it, right now, with the most powerful space telescope ever built, and it is still surprising us. Chapter 13. What 55 Cancri E tells us about planets, There is a final layer to the disturbance of 55 Cancri, one that extends beyond the immediate horror of liquid rock and mineral rain and into the broader question of what planets are. For most of the history of astronomy, planet meant one of a small set of known objects, the 7 classical planets of ancient astronomy, eventually extended to include Uranus, Neptune, and later reclassified to exclude Pluto. These objects defined the category. They were the data points from which intuitions about what planets are and how they behave were built. When exoplanet science began in earnest in the 1990s and accelerated dramatically in the 2000s and 2010s, those intuitions were tested and in many cases demolished. Hot Jupiters should not exist. The standard model of planetary formation said giant planets form in the cold outer system, not the scorching inner system. But here they are, thousands of them. Super Earths, planets larger than Earth but smaller than Neptune, do not exist in our solar system, but they appear to be among the most common types of planet in the galaxy. The diversity of planetary types, orbital configurations, and physical conditions discovered in the exoplanet census is far greater than any model built on solar system data predicted. 55 Cancri sits at the extreme end of that diversity. It is not an extreme example of a type the solar system hinted at. It is a type for which the solar system provides no analog, a rocky super-Earth with a magma ocean surface and a mineral vapor atmosphere, orbiting in a 17.7-hour year at 2.3 million kilometers from its star. Nothing in our solar system pointed toward this. Nothing in our early planetary science suggested that the conditions on 55 Cancri were even physically possible for a rocky planet. And yet, there it is. The implication is not subtle. If 55 Cancri exists, then the space of possible rocky planets is far larger than any solar system-based intuition would suggest. The surface of a rocky planet is not necessarily solid. It is not necessarily cool enough for liquid water. It is not necessarily anything in particular. It is whatever the conditions of its orbit and its host star make it. And the conditions that produce 55 Cancri are not exotic or rare. Any rocky planet that forms and migrates to a very close orbit around its star, a process that the exoplanet census suggests is relatively common, will eventually look like 55 Cancri or some version of it. There may be many planets like this. The rocky planets that orbit closest to their stars, and close-in rocky planets appear, from survey statistics to be common, may very frequently be lava worlds, magma ocean worlds, worlds with mineral vapor atmospheres and geological weather cycles and visible glows from the thermal emission of their own molten surfaces. The planet radius distribution measured by the Kepler Space Telescope shows a curious gap, a region of planetary radii between about 1.5 and 2 times Earth's radius, where planets are relatively rare, separating a population of smaller, denser super-Earths below from a population of larger, less dense sub-Neptunes above. This radius gap, or Fulton gap, is thought to reflect the effect of stellar irradiation on close-in planets. Planets with substantial hydrogen envelopes that orbit close to their stars lose those envelopes through photoevaporation, shrinking from sub-Neptune sizes down to bare rocky cores. The super-Earths below the gap are the bare rocky cores of former sub-Neptunes, stripped of their gas. 55 Cancri sits comfortably below the radius gap, It is a dense, rocky world, possibly a stripped core, in a very close orbit. If the radius gap interpretation is correct, there may be thousands of planets in the Milky Way with similar histories. Former gas-rich planets that migrated to close orbits, lost their hydrogen envelopes to photoevaporation, and now exist as bare, rocky worlds with magma ocean surfaces and mineral vapor atmospheres. 55 Cancri may not be a rare exception. It may be the archetype of a common class of world, a class that previous telescope generations lacked the precision to characterize, and that JWST is now beginning to reveal. This is a strange thought to sit with. When we search for habitable worlds, for planets where liquid water might exist and life might arise, we filter for Earth-like conditions. Rocky planets in the habitable zone, moderate temperatures, possible liquid, water. Those planets exist. They are among the most sought-after targets in exoplanet science. But alongside them, in the same stellar systems, in closer orbits, there may frequently be worlds like 55 Cancri, lava worlds, glowing worlds, worlds where the rock is weather and the ground is fire. Not hostile versions of Earth, but fundamentally different expressions of what a rocky planet can be. The solar system, with its 8 planets and their relatively tame physical conditions, does not prepare you for this. You cannot look at Earth and Mercury and Venus and Mars and infer 55 Cancri. It requires the exoplanet census, the 5,700 confirmed worlds, the statistical picture of planetary diversity across the galaxy, to show you that the space of rocky planet behavior extends to conditions where the concept of a surface dissolves. 55 Cancri is not a freak. It is a data point on a distribution that our solar system does not sample. It is the universe's demonstration that rocky planet is a category broad enough to include objects that have nothing in common with what we ordinarily mean by a rocky planet, except their chemical composition and their approximate mass. Conclusion: the universe has no obligation to be comfortable. We began this video with a number, 5,700 confirmed planets. We have visited 7 of them, in roughly ascending order of disturbance. A cobalt blue world sandblasting itself with supersonic glass. A world with iron weather cycles. A world whose atmosphere is chemically stellar. A world of burning solid ice losing its own atmosphere to a comet tail. A world being stretched into an egg shape and consumed by its star in 3 million year slow motion. A world darker than anything ever manufactured, eating every photon that hits it. And finally, 55 Cancri, a rocky planet 41 light-years away, 8 times Earth's mass, with a global ocean of liquid rock for a surface, a mineral vapor atmosphere composed of the vaporized body of the planet itself, a geological cycle that runs through the atmosphere on timescales of days, and a dayside that glows in visible light from the thermal emission of its own molten ground. The most disturbing planet in the known universe. Not because of a single superlative, not because it holds a record for temperature or wind speed or darkness alone, but because of what those conditions have done to the fundamental character of a world. Not because it is the hottest. KELT 9b is hotter in absolute temperature terms. Not because it is being destroyed the most dramatically. WASP 12b is spiraling into its star. Not because its weather is most violent. HD 189733b's glass rain is arguably more immediately lethal. 55 Cancri E is the most disturbing because it is the most familiar made the most wrong. It is a rocky planet, the type of planet that Earth is. The type of planet that the word world was invented to describe. And on it, the defining feature of a world, the ground, the surface, the solid foundation that makes a planet a place, has been taken by the physics of a close orbit and a hot star, and turned into something that makes the word ground meaningless. When you think about Earth, you think about the ground. You think about it constantly, without noticing, in the way that you do not notice the floor beneath your feet. The ground is the baseline. The surface is the given. On Earth, on Mars, on Venus, on Mercury, on the Moon, on every rocky body we have ever visited or landed on, there is ground. Solid matter that accumulates, that persists, that defines the character of the planet. On 55 Cancri E, there is no ground on the dayside. There is magma, and above the magma, there is not air. There is mineral vapor, silicon monoxide, sodium vapor, oxygen gas. The gaseous remnants of the rock, the magma ocean, is continuously boiling into the sky. The sky is rock, the ground is liquid, the geology is weather. Everything that makes a planet a place has been liquefied, vaporized, distributed through the atmosphere, and carried by the wind to the night side, where it condenses and deposits as a layer of freshly precipitated rock that will, in time, be redistributed back to the dayside by the planet's interior convection. The rock is the atmosphere. The atmosphere is the rock. There is no boundary between them because the boundary has melted. And 41 light-years away, it is glowing, visibly, in the infrared observations of James Webb. We can see its thermal emission. We can measure its dayside temperature. We can watch that temperature change between observations as whatever is happening on its surface and in its atmosphere evolves. We are observing it right now with the best instruments humanity has ever built, and it is still surprising us. This is what 5,700 confirmed planets look like. This is what the universe's exoplanet catalog contains. Not just the familiar worlds that prompted the search. Rocky planets with moderate temperatures, gas giants at safe distances, but worlds that are wrong in ways no solar system intuition prepared us for. Worlds that are the physics of planetary formation taken to its logical extremes and beyond. Worlds that exist because the universe has no obligation to produce only the types of planet that are comfortable to think about. The universe produced HD 189733b because the equations of atmospheric dynamics applied to a gas giant at 4.4 million kilometers from a star give you supersonic glass rain. The universe produced WASP 76OE because the equations of thermodynamics applied to an iron-bearing atmosphere at 2,400 degrees give you iron weather. The universe produced 55 Cancri E because the equations of rock physics applied to a rocky body at 2.3 million kilometers from a star and 2,700 degrees give you a magma ocean with a mineral vapor atmosphere and a geology that runs through the sky. The equations are the same equations that produce Earth's atmosphere, Earth's weather, Earth's geology. The inputs are different. The outputs are alien. Not alien because the physics is different, but alien because the physics is identical. and the conditions are not. The universe is running the same program everywhere, on every rocky body, every gas giant, every icy dwarf. The program does not have a preference for comfortable outputs. It does not distinguish between the quiet blue ocean of Earth on a calm day and the churning magma ocean of 55 Cancri A under a star that fills 30 degrees of sky. To the universe, they are both just physics. 5,700 confirmed planets, 5,700 data points in the distribution of what physics produces when it is given mass, heat, gravity, and time. And at one end of that distribution, 41 light years away, a rocky world that is too close to its star, too hot for ground, too extreme for the word surface to mean anything, glowing, churning, cycling its own geology through the atmosphere, slowly revealing to the instruments of a species that has existed for less than a rounding error of cosmic time, what the universe's range actually is. The number 5,700 is itself a recent and rapidly changing figure. In 1995, we had confirmed 0 exoplanets. In 2009, the Kepler Space Telescope launched, and within a few years had found thousands of planetary candidates. In 2022, the total confirmed exoplanet count passed 5,000. In 2024, the Plateau mission was approved for launch in the 2030s, designed to find Earth-sized planets around Sun-like stars and study them in detail. The Habitable Worlds Observatory, a successor to JWST, currently in early design, aims to directly image rocky planets in habitable zones and search for atmospheric biosignatures. Every new generation of telescopes extends the census, fills in the distribution, adds data points at extremes we had not previously sampled. 55 Cancri E was confirmed in 2004. Its atmosphere was not detected until 2024. 20 years of observations across multiple generations of instruments to characterize a world that was already known. The planet did not change between 2004 and 2024. What changed was our ability to see it clearly enough to understand what it is. There are almost certainly other planets in the current confirmed catalog that are stranger than 55 Cancri E, planets whose full character has not yet been revealed because we have not yet built the instruments to measure them adequately. And there are certainly planets not yet detected that the galaxy's 100 billion or more worlds contain, sitting in their strange orbits, glowing or dark or compressed or consuming, waiting for a telescope precise enough to notice them. The most disturbing planet in the known universe. But the known universe contains 5,700 confirmed planets. The Milky Way contains an estimated 100 billion or more. Whatever disturbing thing 55 Cancri A is, somewhere in this galaxy, there is probably something worse. We just haven't found it yet.